Hi there, my name is Declan Adams, and this is my submission for Lab 4 on springs and oscillations. So to introduce this experiment, the purpose was to examine the motion of a spring mass system in which the mass swings in an arc while also oscillating on the spring. Then we can compare an observed model, which is the spring video, and a predicted model, which is the glow script code, to see if the system obeys the energy principle. So to fully understand this experiment, we first need to discuss some principles. First, we have Newton's second law, which states that change in momentum over change in time is equal to the net forces acting on our system. So here we have the force of the spring plus the force of gravity is equal to our total net forces. And here's the breakdown for each of those two. Then we have the energy principle, which states that a change of energy in a system is equal to the work done by the surroundings plus heat, or added to the system. In this case, both of these are zero, so our equation then becomes the change in kinetic energy plus the change in potential energy of the spring plus the change of potential energy in gravity is equal to zero. And so to briefly preview our results, did the spring mass system obey the energy principle? Yes, and we'll talk about why in just a second. So looking at our models, like we said, our system was the spring mass system, here, force of the spring, and the earth, so gravity, in this direction, with our surroundings being nothing. And so taking a look at our experiment, we first downloaded the provided video and uploaded it to Tracker. Then using Tracker, we went frame by frame to determine the observed position of velocity. Then using GlowScript, we created a computational model that predicted what it should be in terms of position, velocity, and energy. Then we compared the observed and predicted models to determine if the energy principle was upheld. So utilizing Tracker, we can see that the spring mass system moves in a circulatory fashion, creating this oscillatory motion in both the x and y directions. Here are some of the initial conditions that we found and were used in this, with the initial position being found here, and our initial velocity being zero because the system was at rest. Additionally, we needed to find the period of oscillation, which we used this formula for, and looking in the y direction, we used it for one cycle, so we averaged 3 cycles together to find t. Then plugging this into this equation here by rearranging this top one, we found that k was 6.83 newtons. Then to find the relaxed length, we used this equation here to find that the relaxed length was 0.123 meters. So looking at the code, our initial conditions are defined here as the mass of 0.402 kilograms, which we discussed previously. Here's the initial position and velocity that we just mentioned on the last slide. Here's the gravitational constant, here's the spring constant, and here's the relaxed length that we found. These two were just found in that last slide. And for our formulas, we need to specify the vector L, which described both the length and orientation of the spring, so all of that is found here, writing on this equation from Hooke's law. Then we needed to find the system energies, so we found that for the kinetic energy, the potential energy of the gravitational force, potential energy of the spring, and the total energy. And all of this we discussed on one of the very first slides when we discussed the principles. So we also had a calculation loop where we calculated the gravitational force, we calculated the spring force, and we found F net. So all of this is writing on our previously defined formulas. Then we needed to update the spring over time and then calculated the energies over time as well. And so looking at the output, we can see that the GlowScript code generated a spring model using our data where the spring mass system moves in a circulatory fashion over time. We can also see the comparison between our model and our experiment, where earlier in the code we can see that the two line up pretty closely, but over time there begins to become a little bit more deviation, such as seen here and seen here. But overall, we can say that the computational model and the experimental model line up pretty well in terms of position and time, which is a good sign. And so to discuss these results, some sources of error may have been that the center of mass was not correct for every frame. There was over 100 frames, so it is very difficult to get a proper center of mass for each one. Also, because we're using a computational model, it does lack some of the full complexity of the system in a real-world sense, and we're assuming that the work done by surroundings is zero, but in reality this is not true. So to answer some conceptual questions, was the energy principle satisfied? Yes. We want to focus our attention on this orange line, which is delta E. Earlier we said that delta E was equal to 0 because there was no work done by the surroundings and there was no heat added to the system. So we had the change in kinetic energy, the change in potential spring energy, and the change in gravitational potential energy, and all of this summed to 0 at all time points. Additionally, looking at the oscillation periods, we can see that if you calculate the oscillation period for the x direction and the y direction, they give you two different values for k, which means that the direction of the oscillation period changes the stiffness value.